Welcome, everybody. My name is Ricardo Rivera. Some of you might know me as the maintainer for the Charger Drivers API. Also an embedded software engineer at Cirrus Logic down in Austin, Texas. And today I'm going to talk to you guys about how to charge a battery with Zephyr and kind of give a bit of a primer on what charging looks like on portable embedded systems and how to use the Zephyr charging API. So the agenda is kind of broken down into 3 sections, and I'll take maybe like one inline question at the end of each section. There'll be a big green slide. But first, I'm going to go over some fundamentals of charging and what does charging look like, the charging tree on a system. What does it look like? What is a charging peripheral? That's the device that we're interested in today, controlled by the charging API. What is a charge profile, which is the output of the charging device? And then we'll move into the good stuff, which is where does Zephyr come in all of this, and what was there before the Charger Driver API, and how that got upstreamed and mainlined into the Zephyr kernel. We'll take a look at the Charger Device API itself, as well as take a brief stop over at the battery device tree properties. And then complementary to the Charger Driver API, there is a charger sample application in Zephyr, so I'm going to walk through that charger sample application. So let's get into those charger fundamentals. So this is our system in gray, and then our Zephyr host is there in red. And on board the system, there'll be a battery pack shown in yellow. And integrated into that battery pack is the actual battery cell itself, but in parallel to it, there's typically a fuel gauge. And then external to the system is the external power. I just kind of wanted to lay out sort of the nomenclature of this system block diagram first. But now we're going to focus in on the charger or the charger device or the charger peripheral. These terms are kind of, for the purposes of this presentation, interchangeable, but typically this will be an IC, so a dedicated charging chip, or it'll be integrated into a larger PMIC, so a power management IC. It could be a discrete circuit, but it typically isn't these days. And it kind of looks like this. So colloquially, I know that a lot of people refer to the thing that you plug into mains into the wall as the charger, but again, this is the device that lives on board the end system, and on the input side, we provide external power that can come in the form of a barrel jack with like a fixed voltage, those kind of legacy 12 and 9 volt sort of deals. It could be USB, BC 1.2, or USB PD. It could be renewables. Some really fancy charging devices have power muxes, and you can switch between the two. But generically, we provide some kind of external power into the charging peripheral that gets fed into a power converter. That power converter is driven by a state machine that is configured via a control port by the Zephyr host. On the output of the power converter, that's the power that gets sent downstream to both our system and to the battery pack. Architecturally, sometimes these are 2 separate rails, depending on what you want your charger to do. But that's what we feed here out. But focusing back in on Zephyr and the control port, what exactly are we trying to configure in this state machine? So the most important thing is the charge profile. And you may be wondering, what is it? So a charge profile is a set of instructions from the battery pack specification. So the battery pack itself will have a data sheet describing how to charge the battery safely and effectively across a variety of conditions, and kind of spell out the limits and the preferred characteristics of a charging cycle. So the charging peripheral is configured according to the given charge profile from the data sheet to produce the desired output while charging the battery. You might be asking yourself at this point, why even have an API? This sounds very set it and forget it. If it's one battery pack and one charging IC. And you would sort of be right under ideal conditions, but we all know that real life is not ideal, so the charge profile is not static. And real life, the variables, the environmental variables that can play into what your charge profile looks like are things like temperature. Is it too hot or too cold to charge at the maximum capacity that this cell can take? Have the safety timers expired? Is there something strange going on? You're not seeing, the battery voltage rise. And then, finally, our external power could be the blame. So it's not necessarily the battery pack, but, the supply impedance, for example, like let's say if you have one of these very long, convenient 10-foot charging cables, that's a lot more impedance than the OEM recommended 3-foot cable. So this is what a charge profile typically looks like. This is just a generic kind of made-up charge profile that I put here that's typical of a lithium cell, which is kind of the most pertinent chemistry to the applications of Zephyr. So the colored fonts there that you see are the various currents and voltages. Those are the things that we, as the Zephyr host controller, program into the control port of the charging peripheral, and this is what we set according to the manufacturer's specifications. And then over time, as the battery charges, we step through these phases. So looking at the first phase is kind of the conditioning phase. The battery voltage is very low, so the state machine configures the power converter to sync a small conditioning current until the battery voltage rises onto a low battery voltage threshold. At that point, we have seen the battery voltage rise, and the next phase would be the charging phase, where that sunk current is stepped up to a constant charge current, and the battery voltage rises further until it hits the battery regulation voltage target. Again, this is specified by the battery pack manufacturer, and at that point, the power converter is operating in a constant voltage mode, and the sunk current is stopped and allowed to just sort of degrade in this kind of exponential way until ultimately we hit the termination current, which is just a threshold where the current going into the battery has kind of slowed down enough that we can call this battery charged and done. Going back to the block diagram here of the charger device and peripherals, the other responsibility of the Zephyr host here is to set some of the protections. So this charging peripheral, beyond, it's a kind of an application-specific power converter, so it does have some integrated protections typically. So on the output side, some of the protections we can typically set through the control port are overcurrent limiting, so setting a threshold of the maximum current that can pass into this battery pack. Similarly, battery over voltage limiting, and responding to changes in temperature that are sensed by the charging peripheral. On the input side, similarly, again, overcurrent limiting. This would be kind of like a hard comparator cutoff for your system. So it's like a true limit there. And regulation. So the difference between those two is the regulation would be like you know your supply's current limit and you see that you are approaching that limit, so you reduce your charging current in order to keep the supply steady, versus the overcurrent limiting, which is you just got walloped with current and you isolate the system because something's gone wrong. For overvoltage, a little different. Obviously, if you plug in an adapter to a system that exceeds the voltage rating for your system, you want to hit this overvoltage limit and isolate yourself from that supply. But for the flip side, on the regulation, we typically set an undervoltage regulation value to prevent the external power from collapsing. So at this point, That was very hardware heavy. I'll take like maybe 1 or 2 inline questions if anybody's got one. All right. So I'm going to dive into the...
Actually, I have a question for you.
What's up?
So can you briefly explain the advantage? I've used systems where there's a charger that's kind of its own thing. It's not connected to the MCU at all. And what are the advantages of this kind of setup where you actually you can talk to the charging circuitry?
Right. So there are sort of like resistor strapped charging ICs where you just, you place down your various whatever impedance values on a pin and you set some of those thresholds. But this, being able to talk to the charging IC itself has the advantage of being able to respond to certain events in software. So it's not just a fixed static charge profile. There's also, I mentioned it in right here. There's some status info and some telemetry that state machine does expose, and that could be valuable to your specific application and your charging task loop. I think that covers, cool. All right, so let's get into the fun part while you're all here. How do we do this with Zephyr? And let's talk about what was in Zephyr before and touch on the Linux power supply class. So prior to the mainlining of the charger driver API, there is no dedicated interface for facilitating a battery charging cycle. I believe there are some attempts at that in sensors, but nothing like very specific to the application. And a charging API had actually already been proposed in an RFP for the fuel gauge driver API. So if you remember back in the system block diagram, there was the battery pack with an IC on board. In Zephyr, prior to the charger driver API, there was a fuel gauge driver API RFP, and it mentioned a future need for the charger driver API. So I got to cracking on it, and I took quite a bit of inspiration from what exists in Linux. So for those of you that may not know, the way that you do all of what was aforementioned in the previous slides is in Linux, there's a power supply class that provides runtime access to both chargers and fuel gauges, as well as some boot time configuration for fuel gauges and chargers. And the charger driver API and both the fuel gauge driver API took inspiration from the power supply class with some additional tweaks for Zephyr, intentionally so that it would be familiar to anyone that's worked with the power supply class in the past. And this is what the charger driver API looks like. You can find it in charger.h. And it describes these 3 handlers. So we have a get property handler that'll grab a property value from the client driver. We have a set property handler that will set a property value from the client driver. And we have a charge enable handler that is responsible for starting and stopping the charge cycle, which is the execution of that charge profile shown before. And these are the properties that I was referring to in the get property and set property handlers. A lot of these should look familiar to anyone that's used the Linux power supply class. They almost all have the same exact names with charger prefix to it. But additionally, in Zephyr, we allowed for the properties to be extensible to allow for some custom vendor-specific properties. This is a pattern that you see kind of throughout Zephyr where there'll be various properties tied to a subsystem, and there'll be a common count, and then anything beyond the common count is an out-of-tree extension of the existing properties. So on the battery, on the device tree side of things, there's battery.yaml, which describes the static battery characteristics that should be applied at initialization. This is also inherited from battery.yaml in Linux. So we have these basic properties that are specific to the battery pack and that come from its specification. And this DT binding is shared between both the charger driver API and the fuel gauge driver API. There's no need to kind of duplicate that. So they share this common device tree code. So before diving into the sample application, maybe a quick inline question about the charger driver API itself. Going once, going twice.
Sorry, online property online versus property online notification.
That one was added fairly recently. And it's necessary in Zephyr because of that specific comment right above the charger driver API. There it says caching is entirely on the onus of the client. So the online notifier was added because there's a Maxim chip, and I've seen this kind of requirement in some other vendors' silicon where using the interrupt line is required, which is not super common in Zephyr. A lot of times the peripherals are just polling, but for that specific chip, you need to use an interrupt line. And that property is used to call and grab the online value in an interrupt handler, so in the ISR, and then update the cached value. Because in that driver's implementation, when you grab a property, it's just the cached value. So once you get that interrupt, you actually go grab it through that notifier. Awesome. All right. I'm going to go ahead and get into kind of a walkthrough of the sample application for the charger driver API. Right, so this sample application, for those that haven't been, for those that don't know, typically when you upstream an API or a subsystem in Zephyr, you're encouraged to have a sample application to go with it. So we went ahead and did that when upstreaming the charger driver API. And the sample application is just a simple charging task loop that's intended to show system integrators and developers how to leverage the charger driver API for their own applications. It's an infinite loop. The charging task is an infinite loop that's broken out of only when the charging cycle is complete. Inside of that task loop, there's a do-while loop that's just going to poll for external power and a switch case for handling the charging peripheral status. So I'm going to go through this, put up a kind of a flow chart, and then a code snippet showing how it's kind of accomplished. So we enter the task loop, we've probed, we've initialized, and the first thing in the charging task that we ask ourselves is there power connected? If not, don't do anything, wait a while and see if there is power connected. If so, try and charge to the battery. This is what it looks like. Just grab that charger online property, and if it's offline, hop out of that infinite do while and hit the charge enable handler and try and charge a battery. So once you try and enable the charging cycle, the next thing you're going to want to do is check the status to see if you actually did end up charging. So there's 4 different ways that you can go from there. If you did end up charging and the charging device is reporting that you're charging, it's helpful to report the charge type, see what phase of that charge profile you're in, and then check it again. Again, this is just a sample application. It's not telling you how to write your own charging task loop. That's up to the developer. But this is kind of just a generic how to get through a charge cycle kind of a loop here. And so if you enable charging and you see that you're not charging, so that is to mean that there is power provided, you tried to charge a battery and you're still not charging, then something has gone wrong. So you would report the charge health property and see what you would do. So in the case of the sample application, it does nothing because it doesn't go into specifics on how to handle each possible health outcome. Some of those things are really a sign of a system error, like something's gone horribly wrong and you want to stop charging. Some of it is just, you're in kind of a warm spot and you just got to wait it out, and then you will start charging once the fault condition goes away. But in the case of the sample application, it just does nothing. It just reports it out to you and does nothing. If you're discharging, then you go back to the previous slide and you start polling for power again, because that means that the power has been taken away. The external power has been taken away, and there's nothing to do here. And then finally, if you report that the status of the charge cycle is full, then charging is done, and we return 0, and that's the end of the charger sample application. And it's kind of hard to break this switch case and keep it legible, but you can sort of see how that's done here. So going to move on to closing. I don't know if there is any questions about the sample application. Cool. So in closing, some future kind of subsystem improvements for chargers in Zephyr. I'd really like to see, either me do it or the community, a generic GPIO charger driver, kind of getting back to what was mentioned previously about what if the charger doesn't have a control port. That doesn't mean necessarily that there's nothing for Zephyr to do, because a lot of these GPIO standalone charging devices have outputs that indicate, the online status. So it'll be kind of one of those power good outputs, or the output will indicate, it's too hot, it's too cold, or just a generic fault. So in the Linux power supply class, there is a generic GPIO charger driver, and I'd like to see that for Zephyr as well. Moving on to the next point, just like to tidy up the charger sample application a bit and add in more of the properties. On the previous slide, there is way more properties than what are used in the sample application. So part of it would be to kind of abstract it out, tidy it up, refactor it, and make use of as many of the properties as possible, just so that we have kind of full coverage. And a final point would be to add some support for some of the charger telemetry. There's often an ADC on a lot of these charger drivers, so the outputs of that ADC could be useful information, and that does not exist right now. But with that, any final questions?
Thanks for the presentation. Just a quick question. As the API stands at the moment, is it possible to limit the charge to, say, 85% to increase battery lifespan? It's probably to be done in consumer code, or in the code.
Yeah, so that would exist in your... So that would probably be this property right here. So you would just write a value into this in your charging task loop and limit it to 85%. Or you could start out already limited here with this constant charge current max. But this is supposed to indicate like the maximum that your system can take. And some of the charger drivers do clamp to this value, so they'll pick it up from the DT entry, set that as a maximum, and then if you try and write in the application layer, if you try to do a system call and write something higher than that, it's going to say no way, or just clamp. But you can always do less with this property here, just in your application. and respond to. So you would want to reduce for health reasons?
It's actually the capacity rather than the charging current. So say limited to 85% of the full capacity of the battery.
So you would have to do that math on your own.
Okay.
Yeah.
Okay. All right. Thank you.
And each of the properties do indicate, like the ones that are in natural units, they do have the unit suffix here. So this one is microamps. There's microvolts. I think the fuel gauge driver API has more units than that. But yeah, it was kept in these natural units as much as possible.
Hi, yeah, I was wondering how easy is it to add a custom property to this list of already available properties?
Right. So I think there are a couple examples in Zephyr. I haven't had somebody add anything like upstream some vendor-specific properties. Like that is possible. That's something that could be reviewed. There are other APIs in Zephyr that use this kind of architecture. But for out of tree, I mean, it's as easy as just starting, giving it a value after this common count. So these are all, it's an enum with numbers, and any properties that exist after the common count are free to use up until 2 to the 16, so 65535. Does that answer the?
Yeah, that's great. Thank
Cool.
you.
All right. Thank you, guys.